Today's classwork involves watching a YouTube video and reading a bit out of your physics book. So in our new unit on energy forms and changes, it's a mixture of reading out of the book, watching some videos, doing some simulations, and then practicing some skills in class. So what I want to focus mostly on is the reading from your text. You've got 3 pages, and what I want you to focus on, and I want to make some connections to class. So it starts out with a nice general introduction to energy here, and it does connect a little bit to that PhET simulation. It talks about energy comes from the sun. I think we saw that in terms of the sun sending us energy in the form of light, and then the light being able to hit a solar collector, and that light energy being changing form into electrical energy. So there's a connection there. And then you go into this section on work. And work as a term is going to be new for us. But I think when we have an intuitive sense for it takes energy to do work. So it turns out that physicists quantify work not in terms of, oh, I did 3 hours of work and earn this much money. It's not that type of work. There's a particular physics definition that involves, it's got the same units as energy, because when we do work on an object, for example, to lift it up, we did some of that in class earlier this year. When we do work to raise an object, we're expending energy. So in this unit, we're going to formalize our understanding of the term work a little bit. A formula is provided here, and it says that when we consider the quantity force times distance, we're talking about an entire the concept of work. So that's what we're looking for there, force times distance. And in the worksheets that we're going to do, we're either going to lift objects up into the gravitational field, or we're going to accelerate them. They're going to be fairly frictionless objects, and we're just going to give them speed. So that's consistent with what you see down lower here, that there are 2 things that enter into every case where work is done: an application of force and movement of that force. So we're either going to move it up in the gravitational field, or we're going to move it to change its speed. Let's see if I can get onto the other page here. Okay, so here you start to see the formula for work. So here again, you're going to do a fair number of these in worksheets, where you're always given a force. You're going to exert 15 newtons of force on an object, and you're going to lift it 5 meters. So we'll be able to do something with that, a force and a distance. Or you're going to exert 15 newtons of force on something, and you're going to consistently apply 15 newtons of force, and you're going to do so over a distance of 5 meters to accelerate a toy car. So those are the 2 situations we're going to look at. I like these questions here, and there are some textbook questions that are more conceptual. So if you lift a load twice as high, you're doing twice as much work. So I like this particular part of the reading here. That's going to be consistent with some problems that you do. And then this elastic bowstring is a classic example. It, in a way, resembles a bit the idea of lifting something against a gravitational field to pull something back with a string. There's a little bit of a difference there, but what both of those do have in common is you're giving the object potential energy. So when you lift an object against a gravitational field to get it higher, you're giving it potential energy. And when you pull on a spring, you give whatever object is attached to that spring, you're giving that potential energy. Okay, let me move down a little bit. I see I'm 4 minutes into this. I want to keep this around 5 or so. You're going to read about the unit of joules. We've done that. That's our unit of energy. And it also is our unit for work, because work done on something changes its energy. It gives it more potential energy, or it gives it greater kinetic energy in the examples that we're using. Last page, we're going to have you read a little bit about power, and let's see if we can get there. And it doesn't look like I can. Oh, there it is. not to overload you with equations, but power is a rate at which work gets done. So if you do, and I think it's got it nicely presented here. If you're doing a certain amount of work to, say, lift an object up, if it takes you twice as long to do that, then your power is cut in half. So you're not as powerful if it's taking you twice as long. This form of an equation where you have one quantity divided by another equaling a third, that is just, it seems to keep coming up for us. And so there's good number sense and conceptual understanding we can get by just playing around with those. So indeed, if you change your time interval to a bigger number, your power actually goes down. So the concrete example we think of there, again, is if we're lifting a load up a flight of stairs and it takes us twice as long to do it, then we haven't been as powerful. I think we're about at 6 minutes there. That's pretty good. Let me just reduce that and see if that covers the reading. Yep, we're going to have you stop after 8:2. So you'll have some problems out of the book. You'll have a YouTube video to watch. Thank you.